We're chairing the session. Thanks for coming to the session. We have a switch in the first two talks of the session. The order is changed, but everything is in place. Thank you for the speaker for the last minute accommodation. So the talk is going to be about secure sampling with sublinear communication by Song-Girl Choi, Donna Dashman-Solet, Dov Gordon, Lin-Sheng Liu, and Arkady Yerukomovich. And Lin-Sheng is going to give the talk.
All right, thank you all for coming. So speaking of secure sampling, let's consider a study of two-party computation. So suppose we have two parties and they want to sample some information from some joint distributions. This actually comes up a lot. In particular, differential privacy has been studied a lot, where we often sample from Gaussian or Laplacian distributions. And there are also other settings that we also want to sample from private distributions. So there are prior works done this public functions. So what if the probability itself that you want to sample from is shared distributedly across two parties? So assume each of the party has a vector of weights, and the probability function you want to sample from is jointly defined on these two weights. And so, for example, if the function is the L1 distance between the two vectors, that defines the L1 distribution, then that defines the L1 sampling problem. And similarly, we could have L2 and the product sampling and more. So the question is, how can we sample from this privately? Well, a simple answer would be the following. We let one of the party homomorphically encrypt his vector, send over to the other, then we can homomorphically sample from it. This is good, it's easy, and it works well. However, it requires linear communication. So that really raises up a question which we ask in our paper. Can we do this with sublinear communication? So well, with this question in our mind, we started several common distributions. So we construct a sublinear protocol for L1 and L2 distribution. However, for product distribution, we show that it is impossible in general, unless you make some assumptions on those inputs. And from those product sampling protocol, we construct a two-party exponential mechanism as well. So let's see some real protocols, starting from L1. So remember, it's still the two-party setting. And now the probability that the two-party wants to sample from is this L1 distribution defined below. So how do we solve this? Let's take a look at this probability function. This is basically like, so given L1 is linear, this is basically like the summation between the inputs from two parties. And we see that each party can compute exactly one of them. So while this gives us a very simple solution, why not we just let the party one looking at his own input and sample one of the index I1 based on his own local input, and party two samples I2 based on his local input. Then all we need to do is just choose one of them by some coin flip. So this one gives is exactly corresponding to adding those two probabilities together. And the only communication is happening in the third step, which we need to flip a bias coin to decide which one to output. And that gives us correct answer with constant communication. However, this is not private. The parties kind of learn whether the final output matches his coin toss or not. So we need to fix this. Instead of let the party one samples I1 in the clear, we let both parties run a protocol that obliviously samples this I1 for party one and secret share it. And similarly, we can do the same thing for party two. And this oblivious sample protocol is constructed with secure two-party computation and FHE. And this can be done in constant communication. And then similarly, we flip the coin. This time, we flip coin inside the FHE and decide which one to reconstruct and output to both parties. So now, party one no longer knows the I1. Party two no longer knows I2. So with achieving the same constant communication size, but this time, this is secure. This is private. Great. So now we know how to do L1 sampling, which is a very easy case. Now let's have a look at another case, L2 sampling. So exactly the same setting, except now we are going to sample from this L2 distribution defined below. So a question would be like, by looking at this probability function of L2 distribution, we ask, can we apply the same trick from L1? Maybe we just do the same trick, like both parties sample something and output something. However, remember, all we can do for the L1 is because the L1 is linear. But looking at these cross terms, this is apparently not linear. And especially for those cross terms in the denominator, they are actually the inner product between those two vectors. And this is hard to compute. We don't know how to compute that sublinearly. So apparently what we have for L1 cannot be working for L2. We need something new. Well, this is our new trick. We call that corrective sampling. And the whole idea is that instead of directly sample from this L2 distribution, we pick a related distribution, which should be easy to sample with. And we get the index from that distribution, and then we need to correct it back to our desired distribution by a step called rejection sampling. So the whole point is that if somehow this distribution is correlated with the distribution we desire, the desired distribution, then we should be able to get the correct answer, correct output. And for the related distribution, especially for L2 case, what we want to do is to drop those cross terms. So then we can avoid the computing of the inner product. That's what we want. And for this probability pi, we need to correct the index I from the previous distribution. That should be only be dependent on the ith input, which makes this step easy to compute. Otherwise, we are doing nothing meaningless. So now, with this intuition in your mind, let's see our actual protocol. So remember, this is a distribution, I call that a related distribution, which is a distribution A from now. And this is exactly the distribution of L2, dropping all those cross terms. Of course, it's easy to sample from, just using our L1 protocol. You see, each party just locally compute those inputs by square their terms. And this can be done constantly. And then somehow, if we can correct it back with this probability pi, that is the ratio between the L2 distribution, which is what we want, and this distribution A, then we should be good to go. So how do we compute this pi? It seems hard. Intuitively, it seems like it should be as hard as just sample from L2 directly, because I'm basically doing nothing. Well, let's see, can we really handle that? So the pi, remember, the pi we want should be the ratio between these two distributions. And we written the terms by ending with these two terms. Looking at the left term, this only depends on the ith input. Computing of this part is easy. That's just a constant number of summation and a constant number of multiplication. You can run some secure computation protocol and get that part. So how about this right term? This is hard to compute, and we don't know how to compute that. However, like in terms of I from the distribution A, this is constant. So why do we need to compute that? We don't have to. So even though we don't know how to compute it, it doesn't change our output. We still get the correct distribution of L2. So we can just use that part as our pi. Well, of course, you need to adjust that by some constant number to make it a valid probability. So then intuitively, we have a protocol for L2. And sample from this distribution A, as I mentioned before, by our L1 protocol, is constant communication. And with this pi, we can run this. So if you can see, this is the sunshine here. With this pi, we expect this protocol to run an expected constant number of runs. So overall, we will have a constant communication protocol for L2 sampling. And this idea can be easily extended to any LP. So for any P that's larger than 2, it works the similar way. So now we have a sense of L2 as well. How about product sampling? So we should have a talk ahead of me. They will give a definition about product distribution. And now let me give that first. This is exactly the same setting, but this time we want to sample from this distribution we call the product distribution. So how do we sample from that? Again, let's see the probability function. So we see that the probability for some index I being sampled, that is exactly the multiplication between these two terms. This is exactly like the similar thing we saw before, that one party can exactly locally have one of that. And somehow it gives us an idea similar to L1. So maybe we let the party one. So we use our oblivious protocol as well. We let the both party to sample for L1 and then secret share I1 and repeat for I2. So this time we are going to do an equality check. If I1 equals to I2, good, we output it. Otherwise, we restart this process. And this is exactly corresponding to multiply these two probabilities together. That sounds like a solution. However, this protocol has the expected number of iteration that is 1 over the inner product. So that gives us a sense that if you want a sublinear communication, you need to have some assumption on the inner product. Yeah, so we need sufficiently large inner product to make this protocol sublinear communication. And also, since you have assumptions on the input, inherently this protocol will have some leakage. That is the inner product as well. So we can simulate that from the inner product. So now there is another question in general. Can we get rid of this assumption? Can we do sublinear product sampling in general? Maybe some new trick. Well, apparently this time it's impossible. We find it's impossible to do that. We show a reduction from set disjointness problem, which can be shown that it requires at least a linear communication to solve it. So this is for product sampling. And from that product sampling, so we now see that when it's possible to construct that, and in general it's impossible, then we realize a two-party exponential mechanism. The whole point for exponential mechanism is to achieve differential privacy. So assuming you have a list of items H, and the goal for exponential mechanism is to output some of the HI with a probability proportion to the e to the power of SH. Here S is the score function evaluated on H. And the purpose is to hide the individual privacy for the individual item H. So now for two-party setting, assume an additive score function that is collectively distributed among two parties. So in a word, that each party can compute a portion of this score function. And so let's say the party J can compute Sj of HI. And the goal is now to output a common HI with a probability that is e to the power of the total S. And that is equal to the e to the power S1 times e to the power S2. That's given by mathematics. So now, did you see something? This part is exactly two terms. They are multiplied together. One term can be computed by one of the party. This is our product sampling, right? So basically, just plug our product sampling protocol here. You should be able to get the exactly same sublinear exponential mechanism for two party. But don't forget that our protocol, when it works, when it gives you a sublinear communication, it comes with a leakage that is up to the inner product. So our solution would be using a differential private version of JL transform to estimate the inner product to fix this leakage. So now we can achieve a fully differential private exponential mechanism in a two-party setting, and it comes with sublinear communication. So that's basically all I want to say today. And so eventually we brought a question about secure sampling, secure two-party sampling with sublinear communication, and we construct the models for L1, L2, and extend to LP distribution, and we show that when it's possible, when it's impossible for product sampling. And we also realized the two-party exponential mechanism for differential privacy. And that's all I have for today. Thank you.
So we have time for a couple of questions. So I have one. So what if we have distributions that are huge in terms of the number of points, but we have like parameters for them? Like suppose you have parameters of a Gaussian distribution somehow shared between the two parties if they want to sample from it. Does your technique help us how to do it, or is it the easier question by any chance?
I think it depends. It's more like a different question. Like, so for this type of question, it's more like the probability to sample some points has a sort of fixed probability, but distributed among two parties. It's not like a specific version of distribution like Gaussian or Laplacian. And actually, there are prior works done on this type of question, but very few work. Actually, we didn't find any on this type of work. Even though we only like focus on like L1, L2, LP distribution as defined on those two inputs. Well, of course, you can generalize it to any different function. So for example, as you asked, if you have a large Gaussian distribution, and those inputs are just like those parameters are just the inputs from those two parties, that should be the same problem, but that would be a huge, like much harder than the one I showed today. So basically, if you can somehow find a way, for example, there are a bunch of distributions that you can like apply our technique of the get around, like a corrective sampling technique, then maybe you could do that. But other than that, there are tons of distributions you cannot do sublinearly.
What happens if you're willing to compromise and get a distribution that's sort of close to the L1 or 2 product, anything like that, but not exactly?
So I'm sorry.
The output distribution, you want it to be within some statistical distance of your target distribution, but it doesn't have to be exactly the same.
Well, in our in this model, we are more focusing on the distribution that is exactly that distribution. So if your question is asking about whether we can do the distribution that is closer enough to this distribution, so I guess the answer should be yes, because that's more like you're still changing the function f. So remember, our distribution is defined by the function of those 2 vectors. So think about this simpler case. I just randomly wipe away some of those inputs. That gives us a roughly closer enough distribution. So if that met your definition about close enough, that should work. But whether that can achieve sublinear, it still depends on case by case.
What is your rejection probability when you do rejection
sample? So for rejection probability, that should be 1 minus the PI I mentioned. So the PI would be the probability that you accepted that index you sample from the helper distribution.
Thank you very much.
Is there a reason to believe that this is the best possible?
For L2, so there is no best. So basically that gives us expected constant number of runs. So that should be fine. Well, you could always adjust it by some constant, like divided by 2, divided by 3, depends on your need. So that doesn't matter. However, like for the product sampling, even though I didn't call that rejection sampling, you still need to run that many iterations. And the expected number of iterations, as I mentioned, that's 1 over the inner product. So basically, you could say that you need to trade off between the probability for rejection, like to get better communication. And that's inherently that implies to have strong requirements for the inner product or something like that.
Thank you very much. So we need to move to the next talk, which was, thank you very much. Let's thank the speaker again. Thank you very much. So as I told you, the order of the first 2 talks are switched. So we're going to have Nathan now. Nathan Gier. So while the speaker is setting up, let me tell you that Nathan's paper is awarded the Best Young Researcher Award. And let's give it up for the speaker. Is everything okay? Let's wait till.
Down before on the slide. Don't press the last button.
Okay.
You can also use the arrow keys.
Okay, so as I said, this is the Best Young Researchers Award. Let's give it up for him. Yeah, tight computational indistinguishability bound for product distribution by Nathan. Yeah, please go ahead.
Thank you very much for the introduction. So the general theme of today's talk will be about generalizing statistical bounds to the computational setting. So a famous example in this setting, just to give you a general idea of what we are going to do, is Yost-Zoll lemma. So here, what we have statistically is that if we have 2 distributions, D0 and D1, such that when I draw a random bit and then draw from DB and give it to an adversary, asking him to correlate the sample back to B, its ability to do this is bounded by delta. So if I have this, then once I repeat it for k times, once I give him k independent samples and ask him to correlate it back to the XOR of the bits, his ability to do this is at most will decrease exponentially by k to delta to the k. So this holds statistically, and it's not very hard to show using the definition of statistical distance, but computationally, it's more involved because we actually need constructive proof. This proof using statistical distance is not constructive. And computationally, we actually need to show how we take an adversary against the K XOR and transform it efficiently into an adversary against one instance. Now, another comment that I want to make here is that usually we expect to have some slackness here, some computational error. So we may not be able to construct exactly an adversary with delta correlation. Instead, we may only be able to construct an adversary with delta minus epsilon correlation. And we can make this epsilon as small as we want by paying with the running time. So in general, we also care in these types of reductions about the trade-off. We may care about the trade-off between slackness and running time. We will get to it also later. Okay. Now, this was Yost lemma. What is the bound that we are going to generalize? So it's the direct product bound. Let's say that I have two pairs of distributions, x1 and x0 with distance dx, and y1 and y0 with distance dy. Now, what we're going to consider is the distance between x0, y0, that is two independent samples from x0 and y0, against two independent samples from x1 and y1. Okay, so we draw a bit, and either we give the adversary two samples from x0, y0, or x1, y1. Now, it is not hard to show. In fact, it's very fundamental using a simple hybrid argument that the distance will be at most dx plus dy. However, it turns out that statistically it is folklore knowledge in probability theory that you can show that this bound is not tight, and you can actually show something tighter, which is tight, the bound that is dx plus dy minus dx times dy. Okay, so this is the tight bound for two product. If you try to use it again and again in order to get the bound for a K product, what you get is that if the distance between X and Y is D, then you get that the distance between the K products is 1 minus D to the K, which is tight, instead of D times K, which can be even larger than 1. Okay? So what we are going to show is a new direct and simple proof of this tight bound with very good parameters. That is a very good trade-off between the slackness and the running time in the case of non-uniform setting. We also generalize in the uniform setting, but with worse parameters. So before we get to that, why is this bound important? I mean, when do we care about it? So, for example, if D is negligible and K is polynomial, then there's not that much of a difference between them, so we may not really care about it. So really the case where the difference may be more important is when D times K is large. And just to demonstrate to you such a case, I will shortly talk about amplification of weak oblivious transfer. Before that, I just want to emphasize that we already know how to amplify weak OT protocols computationally, but I'm just going to present it so you can get a sense of what types of settings this bound is used for. So weak oblivious transfer amplification originally proved statistically by Damgard, Kilian, and Salveil, and then generalized to the computational setting by Wulschlager. Works as follows. So we have a weak OT. The sender security and receiver security are maybe constant instead of negligible, and we want to amplify them both to negligible. The way this works is using an interchanging application of two operations. We have one operation that amplifies sender security at the expense of receiver security, and another operation that amplifies receiver security at the expense of sender security. Now, the point is that in each of these operations, the amplification behaves like XOR, and the degradation behaves like a direct product. Okay, why is that? So let's look at, for example, the operation that amplifies sender security. So what we do here is secret share the database of the sender into K instances. So its security will be amplified like XOR. Meanwhile, the receiver's choice bit will be constant throughout the K instances. So the security degrades like a direct product because we use the same bit in all the instances. So here it's important to actually use the tight bound, because otherwise you will not be able to amplify the full range of parameters. Otherwise, there will be some non-trivial OT protocols, weak OT protocols, that you will not be able to amplify to full-fledged OT. Okay. Before we get to the actual adversary, I need to mention a few related works. So first of all, Maurer and Tesaro show how to get a computational generalization of the coupling technique and they do this using Holenstein's tight version of the hardcore lemma. So once you have this, you have a general tool of moving statistical proofs using coupling to the computational setting. So we can also apply it here because we can prove this the bound that I mentioned using coupling. And so we can do this and it works. And this is also what Wohlschläger used. But the disadvantage of this is that the adversary is somewhat more involved, and you get worse parameters, worse trade-off between the slackness and the overhead. Also, and I will talk about parameters in a moment. Also, there is a paper by Levy and Rabin that works specifically on this bound. However, their focus was mostly on allowing it to work when there is interaction, on allowing for interaction, and not on improving the parameters. So about the parameters, so for some parameters, for example, if the distance between the K products is expected to be upper bounded by a constant, then what's going to happen here is that instead of increasing the circuit size by 1/epsilon², where epsilon is the slackness, we will only increase the circuit size by log of that. So this is, I think, something interesting here, that often in this setting, I mean, Yau's-Ksoll lemma, direct product theorems, Goldrach-Levin, the hardcore lemma, etc. Usually, the overhead is polynomial in 1/epsilon, where epsilon is the slackness. But here we get something kind of unique. For a large range of parameters, we can get exponentially small slackness with only polynomial overhead. So this is something a bit unique that happens here. Okay, so I talked about simplicity and efficiency. Now let me try to demonstrate it and look at the actual adversary. So the way it works is like this. Just a reminder, what we get is a distinguisher C between x0, y0 and x1, y1. And we want to construct either a distinguisher between x0, x1 or y0, y1. So the first case, the simple case, is if we are able to hardcode some value of x. This is right now the non-uniform setting. If we are able to hardcode some value of x into C and get a good distinguisher between y0 and y1, we are done. This is a simple case. Now, the more interesting case is what happens if this hard coding doesn't work. So, in fact, what we can show is that if the hard coding doesn't work, then the following is a good adversary as a dx distinguisher between x0 and x1. So how does it work? We want to distinguish between x0 and x1. We get as input a value x. We want to know where it came from. What's going to happen is that we start from an initial guess b. It could be 0, could be 1, anything. And then we keep repeating the following. We take b and we sample from yb. Then we use this sample together with x and input it and feed it into C. C gives us the next guess, and then we continue to repeat it. Okay? If you think about it, you can also describe it using the following Markov chain. Now, this adversary, well, it's unbounded, right? You can't actually run it, so you have to stop after t times. So what we actually want to get is the stationary distribution. What we get in reality is just the distribution after t steps. So if you run it for t steps, you will not be able to reach the stationary distribution, but you will get very close to it. And of course, you will need to pay for this distance with the slackness. This is where the slackness comes in. The more time you put in the Markov chain, the closer you get to stationary distribution, and then the less slackness you need to add. Okay? So this is really the adversary. I think it's pretty simple. And there is, and let me just try to quickly describe the main idea. I'm not sure how much time we have left.
1.5.
Okay, so I'll try to go over this quickly. I won't be able to go into details, but the idea of the proof is that we can actually use C to build a distinguisher for an amplifier for distinguishers between x0 and x1. So let's say that A is such a distinguisher, and A is not good enough. The advantage is less than dx. So if you take this distinguisher and you get an x, you build a new distinguisher, you get an x, you apply A, you get the guess B of A. Now you take this B and you use it to sample from YB and feed it into C together with X. So what you can show is that after this step, the difference between dx and the current advantage of A will be multiplied by dy. Okay, so we want to get dx, we get something with advantage that is smaller than x, and what you can show is the difference is multiplied by dy, which is smaller than 1. So you do this again and again and again, and the difference keeps getting multiplied by dy, and this way you get very, very close to dx. Okay, this will be, so the approach will be to start with the trivial distinguisher that always outputs 0, and then keep repeating this step over and over and over again until we decide to stop, depending on what slackness we want to achieve. Now, the reason why this works, the reason why we actually get this amplifier is because of the assumption that C hard-coded with X is not good enough for every choice of X. You can actually look at these 4 distributions, and we know that the distance between x1 and y1 and x0, y0 is at least the advantage of C. And we can use this assumption to bound the distance between the top 2 and the bottom 2. And then what you get is that there's enough distance left for these 2 distributions at the center, which basically says that I can't do the computation right now, but it's not very hard. If you actually subtract from the advantage of C these two differences, you can show that what you get is an adversary with advantage that is better, that is closer to dx by at least a multiple of dy. Okay, so this is just a drawing to demonstrate that, right? We start from the distance dx from dx, we start from 0, and we keep multiplying it by dy. So we get very close to dx, and for the difference, we have to pay with some slackness. So the more time we put in, the closer we are to dx, the less slackness we have to pay. And the last slide, it is actually a straightforward corollary to arrive at the k product bound after you get the isolated case that we've just mentioned. And for this bound, you can still preserve the good trade-off between slackness and overhead of the circuit size. In addition to that, we also show that these ideas also generalize to the uniform setting. It takes a bit more work, but the general idea remains the same. The only disadvantage is that in the uniform setting, you no longer get this good trade-off, this logarithmic trade-off between the running time and the slackness, because intuitively you need to use sampling and testing. And in order to sample and test within accuracy epsilon, you need to work with respect to 1 over epsilon. So this is intuitively why the good trade-off is no longer maintained in the uniform setting. And that would be all. Thank you.
Thank you very much. Let's take the questions while the next speaker sets up. Any questions? So I have one. You mentioned something about the sequential setting. Does your result, you think, potentially generalize to apply to interactive protocols, or you think it's kind of inherent to one message? This logarithmic overhead particularly.
So I think I didn't think about it enough. So I also, sorry, who asked this? Oh, you. Sorry. I looked at, yes. Okay, so I didn't really completely think about it. I do think that because of the nature of this, I mean, I know that the Solemis is generalized to the case of interaction, I think this should also be the case here because in some sense we don't use rewinding. I think that was the problem, but I haven't completely verified it. I do think that it should also be you should also be able to generalize it to allow interaction. So I do think it should work.
Thank you. So there was a question or?
Yeah, but it was very high level. But you said that it's very unique. This logarithmic improvement, exponential improvement, I guess.
Yeah.
For the loss. So you don't have a sense which if there are other applications of the hardcore lemma where people hold.
No. In fact, I mean, it's not like we replace the hardcore. I mean, the hardcore lemma could be used in many places, and the other places we don't know how to improve. Only this one, and I don't know if you can also improve it in other places. I try to think about it, but something is just different there. I don't know. I don't exactly know how to point out what is it, but I tried to think about it in other contexts. For example, Gauss lemma, and I couldn't really see how you could improve it to also have this trade-off in other settings.
Yeah, I think they're lower bounds.
Oh yeah, yes, that's true. Yeah.
Thank you very much for the great talk and the results.
Thank you.
And let's take this again. So the next two talks are shorter. They're technically soft merged. So the first one, and we will take the questions about both of them at the end of the both talks. So the first one is secure non-interactive simulation from arbitrary joint distributions by Hamid Reza, Amini Khorasqani, Hemanta Maji, and Hai Negoyan. And Hamid Reza is going to give the talk.
Hello, everyone. Thank you for the introduction. This is a joint work with my advisor, Hemanta Maji, and my colleague, Hai. So SNIS, Secure Non-Interactive Simulation, was introduced recently in Eurocrypt. In SNIS, Alice and Bob, they want to simulate a joint distribution UV, which we call it target distribution, using n independent samples of another distribution XY, which we call it source distribution. And so more specifically, suppose Alice is given xn, Bob is given by n, and such that xy and xyn is like n independent samples of their source distribution. And Alice, we want to see whether there are reduction functions fn and gn, such that when Alice and Bob they apply those reduction functions on their samples, marginal samples, the distribution of the output u prime v prime is close to some target distribution uv. And we require that this reduction to be secure, which is like for Bob security, xn has no additional information about v prime than u prime. And similarly for Alice security, we can define it. So suppose that Alice and Bob, they output m samples instead of one sample. What is the maximum achievable ratio of the m divided by n? We call it the rate of the SNIS. So SNIS is in fact an information theoretic analog of pseudo-correlation generator, and it is also related to other problems in information theory and theoretical computer science. So I use in this talk I use two notations, BSS and BS. BSS is the binary symmetric source with Philip probability epsilon, but instead of epsilon, I use rho, which is the maximum correlation, and also the same for BS. We use rho, which is the square root of 1 minus epsilon. This is also the maximum correlation. Maximum correlation is some concept in information theory. It is not important that. But epsilon here is the erasure probability. So SNIS was introduced in these two papers in Eurocrypt, and so Agarwal et al. They showed a necessary condition for SNIS of a general target distribution from a general source distribution. In our paper, our focus was in Eurocrypt was on getting SNIS of BSS and BES from BSS and BES and we proved some results for feasibility and rate. But in this talk, our focus is on the case that the target distribution is still BSS BS, but the source distribution is some arbitrary distribution. And we showed that for any constant C and for sufficiently large n, we can see that there is always a perfectly secure SNIS, or we get some C over n insecurity. And we provided some algorithm that we can determine whether perfectly secure SNIS exists or not. And our algorithm also returns a construction in case that such a SNIS exists. For the rate, we proved that any feasible SNIS has constant rate. The rate is not zero. And also, we proved some upper bound on the rate, which the upper bound depends on the maximum correlation of the target distribution and the smallest magnitude eigenvalue of some linear operator associated with the source distribution. But the most interesting result, I can say, in our paper is this one. We showed that there is a source distribution such that SNIS of BSS and BES from that source distribution has the following property, that for any linear reduction, it is infeasible, but there is a nonlinear reduction that achieves the optimal rate. And now I'm going to explain. So this result is interesting because in our Yorker paper, we had also nonlinear reduction, but they achieved the same rate as the linear reduction achieved. So this is that source distribution role. Alice gets sample AB and Bob gets XZ, such that A, B, X are uniform and Z is equal to AX plus B. And our rate upper bound for SNIS of BSS with maximal correlation half is this one is half. And the question is that is this rate achievable or not? The best known construction before our work shows that the rate 1/3 is achievable, but using one round communication. In our work, we don't use any communication and we achieve rate half. So this is the construction. Suppose Alice and Bob, they get two samples of role. So like X1, Z1 is correlated with A1, B1, A2, B2 correlated with X2, Z2. So Alice output, Alice checks whether her samples they form a role, and if that happens, then she outputs +1. Otherwise, she outputs -1. And Bob also does the same. We showed that okay, this is the reduction functions. If you use like minus and 1 instead of 0 and 1, and we see that these are not linear constructions. And we showed that any linear reduction is constant insecure. And this is the summary of our work. So we showed that there is some efficient algorithm to decide and find a construction if such a construction exists. And we proved some upper bound and lower bounds. And we showed that there's a nonlinear reduction that achieves optimal rate. And we use computer assisted search to design efficient protocols. And we proved that any linear reduction for that construction is constant insecure. Thanks.
Thank you very much.
So, I would be happy to answer to your questions after the next talk.
So let me introduce the next talk's speaker and authors. So it's going to be secure non-interactive reducibility is decidable. That's the title. By Kartik Bhushan, Ankit Kumar Misra, Varun Narayanan, and Manoj Prabhakaran. And Varun is going to give the talk.
Am I audible? Thank you. So this presentation is also on in the same model of secure non-interactive simulation, but we will use a slightly different terminology and we'll be calling it secure non-interactive reductions, or SNIR for short, because this is the terminology that we used in the paper. So the main result of this talk is exactly what the title says: secure non-interactive reducibility is decidable. So what is the secure non-interactive reduction problem, or SNIR problem? So we are given two correlations, a source correlation, a target correlation. That is, the source correlation is x comma y and the target correlation is u comma v. And we want to know whether there is a statistical SNIR for securely sampling uv given xy. More formally, we want to know whether for every positive epsilon, there exists an epsilon SNIR that securely samples uv given some n sub epsilon copies of xy. So when we say epsilon SNIR, we mean an SNIR with at most epsilon correctness and security error. And think of this n sub epsilon as an arbitrarily large number. So in order to show that this is decidable, the main theorem that we use states that statistical SNIR is going to imply perfect SNIR. So what does this mean? So the theorem states that there is a statistical SNIR for uv given xy only if there is a perfect SNIR with perfect correctness and perfect security that samples uv using n sub 0 copies of x comma y, where n sub 0 should be thought of as a constant that is decided by the description of the correlations uv and xy. Now, as a immediate corollary of this, we get that the SNIR problem is decidable. Furthermore, if there is a statistical SNIR, then there is an algorithm that actually outputs a perfect SNIR for the same problem. So going from the theorem to this corollary is rather straightforward. So we can build an algorithm that takes the description of the source and target correlations and computes this number n sub 0 that's given in the theorem. And then it searches through all possible, reduction functions, or what we call protocols, and sees if there is a perfect SNIR taking xy to uv. If there is one, then the algorithm can always output a perfect SNIR. And the theorem states that if there is none, then the statistical SNIR itself is impossible. So because we don't have a lot of time, I will try to give a brief intuition behind how we show that statistical SNIR is going to imply perfect SNIR. So so let's start with a protocol that is an SNIR protocol A comma B that realizes an epsilon SNIR securely sampling a copy of the target correlation using, say, n copies of the source correlation. So think of D and C as the probability mass functions of these two correlations. Jumping ahead, what we are going to show is that these two reduction functions or protocols A and B, they look only at a constant number of copies of the C that is taking as input. Remember, it's taking n copies of the correlation as input. But what we are saying is that the protocol A effectively looks only at a constant size subset of these n copies. And this constant is going to depend on the description of the source and target correlations. But now what this means is that if there is a statistical SNIR for D using C, then for every epsilon positive, but however small it is, there is a protocol that uses only a constant number of copies of the correlation and gives you an SNIR that is less than epsilon, that has less than epsilon security and correctness error. But this, since there are only a finite number of protocols that take n copies, I mean, like the constant number of copies of C and does a reduction, this should mean that there should be a protocol that is realizing perfect SNIR. So what goes into this? How much time do I have?
1.5 minutes.
So what goes into this? So we start with a certain notion of spectral protocol. That is, so A has a linear transformation that gives you a so-called spectral protocol A hat. And we realize that this A hat is in some sense, a Fourier transform of the protocol A itself. And then we note that this A is so that the Fourier transform concentrates most of its energy in like low degree coefficients. That is, it concentrates on basis functions, each of which depends on a few number of variables. But then this is perfect for us to apply a Junta theorem that says that if this is the case, then A should be a function that depends only on a few of the few of the coordinates of the function itself. So we could not find a Junta theorem that works for a generalized Fourier transform of this kind. So we stated and proved such a Junta theorem, and this might be of independent interest. And yeah, this is how we show that there exists a perfect SNIR for D using C if there is a statistical SNIR. So in conclusion, we showed that statistical SNIR problem is decidable. There are two interesting open problems. The first one is about the rate of statistical SNIR. It's still open to characterize the exact rate of statistical SNIR. And the other one would be to think about what would happen if we allow interactions, what kind of results can we get? And this would relate directly with OT complexity of a function computation and so on. Thank you.
Thank you very much. Quick questions for Ahmad Reza and Aaron. If you have a question for one of them, specifically mention it. Otherwise, I guess it's to both of them. Questions? You had any questions? I ask what for natural distributions like OT, joint OT correlations, do we have a characterization of what correlations imply them? For things that we care about, particularly say OT, or is it a very hard question?
So an earlier work had talked about what are some necessary conditions that are directly that can be directly used to tell whether there is a SNIR from a source to a target. But then so if we look at this particular result itself, it is talking about a number n sub 0, which could be potentially really large depending on the description of the two correlations. So it's not easy to run a program to find this.
So you show it's decidable, but for specific cases, do we have like nice?
So there are a few set of results that says that the OT correlation cannot be realized using binary erasure correlation and things like that.
We know some cases. Okay, got it. Any other questions? So before finishing the session, just be aware that this break is actually shorter. It's unfortunate that this time that the break is shorter. We are ending later than the typical time, but the break is going to be about 15 minutes, I guess, a little bit even shorter than that. Any other question or otherwise, let's thank both of the speakers and all the speakers of the session.